Okay, welcome everyone to my continuation of what is geometric topology. Today we would like to play a little bit more with surfaces, but we would like to make it even simpler in some sense by reducing this two-dimensional idea of a surface to a very one-dimensional idea, namely to the idea of using words for surfaces. In some sense, how to read surfaces. Okay, as a reminder, surfaces combinatorially are usually just polygons, and polygons have edges, and the edges are have some labels, maybe just some letters, A, B, C, whatever. So we can easily form a word by using the following trick. We just start somewhere. Let's say we start here, and we read in a certain direction, and just read off the edges, remembering the orientation. That's the only tricky part. We also remember the orientation. So let's see. So A, D, B, C inverse, A, D, B. Let's put an overline for the inverse. C inverse, E, C inverse, and so on, right? F inverse, and so on. And we get a word from the surface, which remembers kind of the order of the edges, so which edge we see, and also the direction, because we're using this overline to keep track of whether we run against the orientation or we run with the orientation. And there are some choices involved. I could also read clockwise or whatever. But anyway, let's use this definition. And what we get is called the surface word. Okay, so the question is, how much information about the surface is actually contained in the word? Turns out quite a lot. So first of all, we need to kind of find some relation. Some words might give the same surface. And one relation is relatively obvious. So I call it the necklace relation. So it really means just cyclic permutations. You should think of, well, that's exactly the picture, right? The edges are like pearls on a necklace, if you want. And it doesn't really matter where you start counting. You kind of get the same answer all the time. If I would start counting here and go all the way around, it's just kind of permuted. In a very simple case, ABC is the same as CAB is the same as BCA. You just permute the letter through, thinking of it as being on a necklace, and that really shouldn't give a different surface, because it just corresponds to me choosing a different starting point, and the surface just doesn't see that. It stays the same, right? The polygon doesn't change. Whether I choose a different starting point or not, the polygon doesn't care. So that's certainly a relation we want, and we really should think of those words not living on a straight line, but living on a necklace. Right? It lives on a circle, and that's one of the crucial relation here. And I call it the necklace relation for the obvious reason that I would like to. Well, maybe it's not obvious, but I would like to think of them as being a necklace. But of course, you could also say they just live on S1 or something, right? And a necklace, mathematically speaking, is nothing else than a circle. Okay, and a few more relations that appear here, and then I will give you kind of a classification of surfaces in this way. So another relation, and that's a bit subtle, and if I do this in practice, I don't want to talk about you, but if I do this in practice, I always get that wrong. It's not so bad, so let's see. The free edges, these are the edges that are not paired. Okay, so in this picture, for example, A is paired, so there's an A and another A, H is paired and so on, but they are the free edges B, F, and G. Okay? So they are just single edges. Okay, and they might correspond to boundary components, but they also might collapse. They might be one edge secretly, and you can't tell that in the polygon until you have checked. And what we do here is, for example, the following. We just check the endpoints. Let's call the endpoint of B, let's call it X. Since this is also the starting point of D, X is also down here, right? So this is kind of the tricky point. The X up here is certainly also down here. And since this is the endpoint of H, it's also up here, and so on, and so on. And it turns out that D well, let's say D is an edge from Y to so B is an edge, D is an edge from X to Y, then B is also an edge from X to Y. So B is an edge from X to Y. Okay. And then you just do this and just label the vertices as well. And you will see that G is an edge from X to Z, different vertices, and my remaining one F is actually an edge from Y to Z. So if you compose them, ignore the orientation in this case. So I could also think of B going in the opposite way from Y to X, and then you can just compose them. So B goes from Y to X, all right, and G goes from X to Z, and F, let's say, goes from Z to Y. So secretly, all of these are the same vertex. They're just arranged strangely in the polygon. Okay, so let me say it again. What you need to do in order to find this relation, and that's always tricky. As I said, I always get it wrong. It's not so bad, but here it goes. You need to identify what vertex is actually the relations among the vertices, and then you can just check whether edges actually are just one long edge instead of multiple edges. So that's what you need to do. And because it's just one long edge, these kind of should be counted the same in the necklace reading of the word. And that's kind of almost everything you need to do. And then you're almost done. So let's say you have a closed surface, and let's just be not forever. This is not a really restriction. It just makes a statement nicer. On the next slide, I give you the general statement. But let's say we have a closed surface which is not the sphere, then the surface is of the following form. It has H, a certain number of handles, right? It's this hash product of the torus, and it has a certain number of projective planes, P, again, a hash product, so the connected sum product of surfaces. And then you can just write down standard words. So a lot of words correspond to the same surface. There's some relations, but there are standard words that you can cook up. For example, the 3 times torus, which in the picture is just 3 handles, right? H is a number of handles. I will have a picture for P as well in a second. P is always a bit tricky, so P is not so easy to imagine. But 3 handles, I think I can handle 3 handles. So here's a picture, and the reading word, the standard word, is here's the first handle. It's A inverse, B inverse. Here's the second handle, same pattern, CD, C inverse, D inverse. And here's the last handle, same pattern, EF, E inverse, F inverse. Okay, and so on, right? If you have 10 of them, they just continue. The projective plane is even easier. It's just AA, BB, CC, DD, and so on, right? So 3 here's AA, BB, CC. So here's the first copy, here's the second copy, here's the third copy. So projective planes are actually easy as a word. So it's A1 and so on. And this one always alternates. And these are the standard words for those surfaces. And then you just paste them together and you get a bigger surface, and just count the number of those guys, that's H, and count the number of those guys, that's P. And every closed surface, which is not a sphere, is of this form. The general statement then needs to take those guys into account. And here's a general statement. So every surface is of the following form. You have a certain number of punctures, which I call, for historical reasons, actually I don't really know why, but I call it D, and a certain number of handles and a certain number of projective planes, and they're all kind of hashed together. And a puncture, so from left to right, here are the pictures. So this is a punctured sphere, for example. That would be S hash 1 copy of D, so S hash D, so D is 1, and everything else is 0. A punctured sphere is really just a balloon with, well, the puncture is where you will actually blow air into. So that's a punctured sphere. And here's a sphere with 3 handles. Slightly better picture than this one. They're of course the same, but you can really see how I attached, or how whoever made this picture attached the handles to the surface. And the projective plane thing is a little bit harder to imagine because it doesn't really live in 3 space. It only lives in 4 space. But let's say, well, you can kind of see it in the picture. Let's say it's just glued in a Möbius strip, right? The Möbius strip does the inversion here around this line. And that's just what it is. So let's say you just glue in a nice Möbius strip into the sphere. And you have this really kind of really compact and nice statement that every surface is just essentially determined by 3 numbers: the number of punctures, the number of handles, and the number of projective planes, which is then the general classification. And then you can put those words together with these rules, and you can just read off from the word, which might be a bit tricky because those words get a bit tricky, but for a machine, for example, it's really simple. Anyway, so that was the classification of surfaces, and it's kind of via polygons or words. Depends a little bit how you would like to think about it, but it's really simple. There are only 3 numbers: punctures, handles, and then those funny Mobius strip type objects, the projective planes. Anyway, I hope you enjoyed the video, and I also hope to see you next time.